Hello and welcome to the next of the lectures in this week 4 in the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. So far, we have seen a generalization of the classical implication to the fuzzy setting. We have seen how to decode the axioms that we have come up for in terms of the definition of a fuzzy implication from a geometric perspective. That is, we have looked at how the 3D plots of fuzzy implications would look like, what are the essentials there. We have also seen some desirable properties that we expect a fuzzy implication to have. Specifically, we have seen how to obtain fuzzy negations from fuzzy implications. In this lecture, we will deal with how to construct fuzzy implications. There are myriad ways of constructing fuzzy implications. It is still a very hot research topic to come up with families of fuzzy implications satisfying some specific properties. In this lecture series, we will only single out two particular ways of constructing fuzzy implications and discuss them in detail. The first of them is to obtain fuzzy implications from existing or known fuzzy logic connectives. In our case, we have seen t-norms, t-conorms and fuzzy negations as the fuzzy logic connectives so far. So we will try to construct fuzzy implications from these three fuzzy logic connectives. We could also construct fuzzy implications from unary operators, much like we constructed t-norms using additive generators, which are themselves just unary functions. Once again, we know that this is the truth table of the classical implication. Based on this, we have come up with the definition of fuzzy implication as follows. A binary function on this 0-1 interval, which is mixed monotonic. That means it is decreasing in the first variable and increasing in the second variable. Once again, not in the strict sense. And we ask for the boundary conditions, these four boundary conditions, which are essentially what appears in the classical implication truth table. Now, let's look at these two conditionals. By now, these are very familiar to you. And we ask this question, when is a conditional, when is this or these conditionals true? We have seen that these are true, or any conditional can be considered as true if either the antecedent P is false or Q is true. Now, this could also be equivalently formulated in terms of classical logic operations as follows. P implies Q is actually equal to negation P or Q. Note that whenever P is false, negation P will make it true, which means true or something else would be true. Now, are we justified in capturing this essence through this formula? Well, let's look at the truth table for the classical implication. This is what we had as the output or the truth value of the implication P implies Q, the conditional P implies Q. And now, if you actually apply this formula, negation P or Q, for the corresponding values of P and Q, we see that both these values coincide, and for all possible combinations of P and Q. And since we are talking about binary logic, classical logic, we have only four possibilities combined for P and Q, and we see that all of them are actually coinciding with what we have as the truth table for classical implication. So it appears that this is actually a valid formula to capture when a given conditional will have a particular truth value. Once again, recall that we are discussing truth values of compound statements in the sense of being able to construct them from the corresponding truth values of the components. This particular formula, which in the classical logic setting is called the material implication, led to introducing the first, perhaps the first family of fuzzy implications themselves, which are called SN implications. Let's look at their definition. So now we had negation P or Q, so we need a negation and we need a disjunction, which in the case of fuzzy logic connectives or fuzzy set theory will immediately translate, or at least used to translate, into T conorms and negations in the early days of research. So we start with the T conorm S and a fuzzy negation N, and define a function I as follows: S of nx comma y. We will denote this as I with subscript Sn. So ISN is what we would denote this as, and consider this function. It is easy to see that ISN is a fuzzy implication for every T conorm S and any negation N. Let's look at this. This is the formula we have. For this to be an implication, what we want is ISN should be decreasing in the first variable and increasing in the second variable, and should satisfy the boundary conditions. Now let's look at this. If we fix y, let's fix y and increase x. As x increases, we know that n of x decreases, and s is an increasing function. So in the first variable, as n of x decreases, for a fixed y naught, s also will decrease. That means this property is valid. Similarly, if you fix an x naught and increase y, then we see that s of, as y increases, s will increase because s is an increasing function. It's a monotonic function in both variables. It is commutative anyway, so if it is increasing in one, it is also increasing in the other. So we see that both these properties are immediately satisfied. Now what about the boundary conditions? Let's look at this. ISN of 1, 0 is nothing but s of n of 1, 0. This is s of n of 1 for any negation. N of 1 is 0. So s of 0, 0 is 0. Similarly, we can show that s of 0, 0 is nothing but s of n of 0, 0. N of 0 is 1. So it is s of 1, 0, which is actually 1. So similarly, we can check it out for the other boundary conditions, and you will see that we actually get that all the 4 boundary conditions are indeed satisfied, and this ISN is a fuzzy implication. A word about the nomenclature. In the beginning, early days of research into fuzzy implications, people typically considered strong or involutive negation, and in such a case, ISN was called an S implication instead of an SN implication, where the N was strong. Let's look at some examples of SN implications, and you will immediately see on the rightmost column that you have the familiar basic fuzzy implications appearing immediately. Let's take a couple of them. Here SM stands for the maximum T conorm, and NC is the usual classical negation 1 minus x. Let's use this formula and see what is it that we get. So SM of xy is max of xy NC of x is 1 minus x. So let's look at what is ISM comma NC of xy. This is max of NC of x comma y, which is nothing but max of 1 minus x comma y, which as we know is essentially the Kleene-Bill's implication. So you see here that 5 of the 9 basic implications that we consider are in fact SN implications. Perhaps we'll take one more. We have the SP T conorm, which is given like this. This is the dual of the product T norm, and once again we consider classical negation 1 minus x. So now ISP NC of xy will be, instead of x we have to put 1 minus x plus y minus Instead of x, we have to put 1 minus x into y. This turns out to be 1 minus x plus y minus y plus xy. And we cancel, what we get is 1 minus x plus xy, which is essentially Reichenbach implication. That's what we have indicated here. And similarly, if you work out for the rest of them, you will get these SN implications. Note that interestingly, if we consider ND2, which is the largest fuzzy negation that you could have, which is 1 almost everywhere except at the point x is equal to 1, and any T conum S, we will get the Weber implication. Just to recall the geometry of these fuzzy implications, how their 3D plots would look like. Look at this. This is the Reichenbach implication and this is the Łukasiewicz implication. These are once again SN implications. In fact, you could call them S implications also because they're the negations that they are being obtained from are strong negations, 1 minus x. There's the Fodor implication. This is the Weber implication. This is the Klein-Leins implication. On the right, you find another implication. However, it is not an SN implication. The reason for that would become very clear if you want one immediately. Okay, so let's look at the SN family of implications from the perspective of what desirable properties they satisfy. And we have listed out 4 such desirable properties so far in the previous lecture. The first of them is the neutrality property. That means when x is equal to 1, then I of 1 comma y should be equal to 1. Essentially, we saw this was discussing about the right boundary of the implication from the perspective that we have. That means we are looking at the right boundary of this particular region from the perspective that we have. The neutrality property is I of 1 comma y is y. Next, we discuss the identity principle, which talks about what should be the value that the function, the implication should assume when you walk along the diagonal. That means y is equal to x line. If it is 1, we call it a fuzzy implication that satisfies the identity principle. The ordering property extends this and says that it will not only be 1 on the diagonal. Clearly, because of mixed monotonicity, it can be proven that above the diagonal also it is 1. But ordering principle says, the ordering property says that it should only be 1 up to the diagonal and not beyond it. That is what is insisted by this if and only if condition. Finally, we saw that exchange principle is some kind of, it might remind you of associativity. It is related to associativity when you generate fuzzy implications in a particular way. For example, SN implications, they derive that they have this property exchange principle through the associativity of the underlying T conum. We will see that presently. The exchange principle says that if you have I of x comma I of yz, you could essentially interchange y and x, and this will be equal to I of y comma I of xz. So this is where the nomenclature of calling it an exchange principle or exchange property comes into picture. Now, the next few slides will discuss what are these, what properties from these an SN implication is likely to have. First thing that you can see is that an SN implication always satisfies neutrality property and the exchange principle. Remember, exchange principle is not easy to see in terms of geometry, but we will try to prove it very simply. So ISN of xy is given like this, S of n of x comma y. Note that neutrality is this property, and clearly if you put ISN of 1 comma y, it is nothing but S of n of 1 comma y, which is S of n of 1 is 0 comma y. We know that 0 is actually the identity for any T conum, so you will get y. Let's look at the exchange principle. What does it say? I of x comma y, x comma y, I of y comma z is I of y comma I of x comma z. This is what we need to prove for the SN implication. Let's consider the LHS. Now if we substitute slowly, then what we have is, let's unfurl from the inside. So this is S of n of y comma z. This will be S of n of x comma S of n of y comma z. Now we know that S is a T-conorm, which means it is both commutative and associative. So now, using this, both commutativity and associativity, we can write this as S of n of y comma n of x comma z. Now what is this? Once again you see that there is nothing but S of n comma y. Now this part I can write it as I of x comma z, or I Sn of n comma x comma z. And now this is nothing but I Sn of y comma I Sn of x comma z. And this is essentially what we wanted to prove as the exchange principle. So as you can see, the associativity and commutativity of the T-conorm, underlying T-conorm, really helps us in ensuring that the fuzzy implications have, SN implications have the exchange principle. What about the other properties of IP, the identity principle or the ordering property? It can be shown that they do not always, the fuzzy implications coming from this family do not always satisfy IP or OP. If you ask the question, when do they satisfy either of them or both of them? Well, we need to discuss a particular functional equation, which we have seen earlier, if you recall, as the law of excluded middle when we discuss lattices. We will have a separate lecture on discussing functional equations involving the fuzzy logic connectives. So for the moment, we will skip this part about discussing when do they have IP or OP. Finally, if you look at the natural negation of an ISN, what would it be? Now, what is natural negation of an implication? Given an I, n of I of x is nothing but I of x comma 0. So in the case of ISN, this would be ISN of x comma 0. This is nothing but S of n of x comma 0. Note that 0 is actually the identity of the T-conorm, of any T-conorm. So what we get is, it is n of x. So the natural negation of an SN implication is nothing but the negation that you originally employed to generate this fuzzy implication. Let's look at some of these SN implications and see what properties they have from a geometric perspective. So now this is the Reichenbach implication. You see that it has the neutrality property. That means that x is equal to 1, you have this y. If you look at what is its natural negation, you see clearly it is 1 minus x. That can also be seen by putting y is equal to 0 here, you get 1 minus x. If you put x is equal to 1 here, you get it is y. And so is the case with Łukasiewicz implication. However, in the case of Łukasiewicz implication, you see that it has the identity property. That means along the diagonal it is 1. In fact, it has ordering property also, because it is 1 only above the diagonal and now below it from our perspective, so to speak. Whereas the Reichenbach implication neither has IP nor OP. This is the Fodor implication. Once again, it's an SN implication. You can see that it has a neutrality property as any SN implication would have. Its natural negation is 1 minus x and it has both OP. If it has OP, definitely it also has IP. And this is the Weber implication. Once again, you see that it has this neutrality property. The natural negation is ND2, the largest one. And you see here, along the diagonal, if you travel, it takes the value 1, but it does not have the ordering property simply because even when x is greater than y, I Weber of x comma y is actually equal to 1. There's the Klein-Dientz implication. Once again, you see that it satisfies neither IP nor OP. This the other implication that we have seen a little while earlier. You see that it cannot be an SN implication because it does not satisfy the neutrality property. However, it has such a formula. So it essentially max of 1 minus x comma y square. So you can look at it as S of nx comma y square, where n is the classical negation and the T quantum S is the maximum T quantum. However, this is not classified as an SN implication, even though it's a fuzzy implication. Well, so far we have discussed constructing fuzzy implications from other fuzzy logic connectives. Specifically, we have looked at the family of SN implications. Clearly, the notation SN here stands for T quantum S and the negation N, from which such implications have been obtained. We have also discussed that the properties that they satisfy, specifically the neutrality, identity, exchange principle, and the ordering property. And interestingly, we found that the natural negation of an SN implication turns out to be the original fuzzy negation from which the fuzzy implication itself was constructed. What next? There are many such families that we could construct. We will look at two other families of fuzzy implications constructed from fuzzy logic connectives, namely the families of R implications and QL implications. R implications are perhaps one of the most important families of fuzzy implications. Their importance can hardly be exaggerated. And QL implications, they actually find their inspiration perhaps from the quantum logic setting. We will look into both these families as we have done for SN implications. That is, in the next lecture again, we will look at constructing fuzzy implications from fuzzy logic connectives. Constructing fuzzy implications from unary operations will be taken up in the next lecture following that. And for the topics that we have covered in this lecture, a good resource could be the book of Fuzzy Implications. Glad that you could join us today for this lecture, and looking forward to meeting you in the next lecture. Thank you once again.